Hello everyone, this is Power Series Solutions Part 4. So, last example, situation where we now look at second order differential equations. So we know we had the assumed solution, we've used the first derivative, and now here's the second derivative. Notice how the index changes from to 2, and it's almost like we just took the first derivative term and differentiated it, where n, c sub n are constants. Swing down the n minus 1, so we get n minus 1, c sub n, x to the power 1 less, then n minus 1 would be n minus 2. So the reason for this is basically just looking at the series in expanded form. If we consider that y prime, we already have that, so let's start with that. In expanded form would be when n is 1, we'd get 1 c sub 1 x to the 0, or just c sub 1, plus when n is 2, 2 c sub 2 x to the 2 minus 1 is 1, so just 2 c sub 2x, plus when n is 3, 3 c sub 3, because again we're just replacing n by 3 here, x squared, go further if you like, 4 c sub 4 x cubed, and so on. So if we literally just took the derivative c sub 1, 0, we'd get 2 c sub 2 as a constant, derivative x is 1, plus, and then this would be 6, or maybe I should write 3 times 2, c sub 3 x to the first, or just x, and then here let's write 4 times 3 times c sub 4 x power 1 less squared. And now we can see how that represents the sum that we indicated. If we start at 2, then the first coefficient has to be 2. And that is taken care of by n times n minus 1, because you'd have 2 times 2 minus 1, so that's just your 2. And then c sub 2 here would be when n is 2, so it's c sub n. And then x to the n minus 2, when n is 2, that'd be x to the 0, which is just 1. So it appears to work for the first term. Let's see if it works for the second term. Notice that it's 3 times 2. When n is 3, that would be 3 times 2, c sub 3, 3 times 2, c sub 3, x to the 3 minus 2 is 1, and you can verify it for this term as well. When n is 4, we get 4 times 3, c sub 4, there's 4, 3, c sub 4 would be x squared, and there it is. So that's a little justification. Alright, so now we can, we've got the 3 things, and we just substitute, as always. So now y double prime is the sum as n goes from 2 to infinity of n minus 1, c sub n, x to the n minus 2. And that's equal to 4 times y, which is the sum as n goes from 0 to infinity, c sub n, x to the n. Okay, there's no variables out in front. Last time I saw a variable out in front, one of the sums, and we had to distribute it, but there aren't any. But if there are, pay attention to that and distribute accordingly. So now let's note about the x powers. X powers differ by n compared to n minus 2, so that's 2. And the indices differ by compare n equaling 2, starting point, to n equaling 0. They differ by 2 as well. So remember, when these differences are the same, just a simple shift will get us to a point where we could use the identity principle, as opposed to the last example where we saw that we had to count off. So you always want to shift the higher index down, and we'll have to shift this one down by 2. So we get the sum as n goes from 0 to infinity. Okay, if we shift down by 2, that means that each of the values of n in the defining equation for the nth term, those values of n will increase by 2. So this n becomes n plus 2. The n minus 1 becomes n plus 1, because n plus 2 minus 1 is n plus 1. The c sub n becomes c sub n plus 2. And the x to the n minus 2 becomes just simply x to the n, because x to the, now n is n plus 2, minus 2 is just n. And then this right side we just leave alone. Okay, so now looking at that, we see we could use the identity principle, because the indices are the same and the powers on the x are the same. So then just take out the coefficients. Don't forget the 4. And so we could state that n plus 2 times n plus 1 times c to the n plus 2 is equal to 4c sub n. And then we get our recurrence relation. That c to the n plus 2 is equal to c sub n plus 2 is c sub n, well actually 4c sub n, over n plus 2 times n plus 1. So there's our recurrence relation. And notice that the values of the subscripts differ by 2. So therefore we're going to have some even and odds again. So the evens will be in terms of c sub 0, and the odd in terms of c sub 1. So I'll start with the evens. That means n is 0, 2, 4, 6, etc. And when n is 0 into the recurrence relation, we see that c sub 2, because n is 0, would be 4c sub 0 over, this would be 2 times 1, because n is 0. And I think that might be nice to just leave that, because getting a feeling of factorial in the denominator, let's see what goes on when n is 2. That would be c sub 4. And so when n is 2, c sub 4 is 4, c sub 2 over, now n is 2, so that's 4 times 3. But now c sub 2, we got 4 over 4 times 3 times c sub 2, which was 4c sub 0 over 2 times 1. So it looks like 4 squared c sub 0 over 4 factorial. Okay, at least we'll need c sub 6. And that might actually be sufficient. So let me go here. For c sub 6. And that would be when n is 4, so that's going to be 4c sub 4 over n is 4, that would be 6 and 5. So that'll be 4 over 6 times 5 times c sub 4, which was 4 squared c sub 0 over 4 factorial. So it looks like we've got 4 cubed c sub 0 over 6 factorial. Okay, and then you could find more terms if you want. Let's do the odds. So now n is 1, 3, 5, and so on. Okay, when n is 1, into the recurrence relation again, we see c sub 3 is 4 c sub 1 over n is 1, so that's 3 times 2. Now when n is 3, c sub 5 would be, again, n is 3 in the recurrence relation, so c sub 5 is 4 c sub 3 over, when n is 3, we get 5 times 4. That's 4 over 5 times 4 times c sub 3, which was 4 c sub 1 over 3 times 2. Probably should have just called this 3 factorial, because obviously now we've got 4 squared c sub 1 over 5, 4, 3, 2. Add a 1, you got 5 factorial. Okay, and then we'll just do c sub 7. It's going to be 4. Now that's when n is 5. So c sub 7 is 4 c sub 5 over, when n is 5, that's a 7, that's a 6. So that's 4 over 7 times 6 times c sub 5 was 4 squared c sub 1 over 5 factorial. So that gives us 4 cubed c sub 1 over 7 factorial. And you could generate more terms if you wanted to. Okay, so now our solution, y, which was the sum as n goes from 0 to infinity of c sub n x to the n. Okay, it's normally c sub 0 plus c1x plus c2x squared plus c3x cubed, and so on. But now, because we've got both even and odds giving us different factorials, different terms, different coefficients, I should say, in patterns, we should separate this. So maybe we want to write that y is, this might be a little bit awkward in terms of the notation, but c sub 0 plus c2x squared plus c4x to the 4th plus dot dot dot, and then a big plus, and then c1 plus c3x cubed plus c to the 5th x to the 5th plus dot dot dot. Okay, meaning that these are the evens and these are the odds. And then if you want to show the literal substitution, okay, first off c sub 0, so now everything in terms of c sub 0, c2 was 4 over 2 factorial c sub 0, and that's x squared, plus c sub 4 was 4 squared over 4 factorial c sub 0, and that's x to the 4th, plus, let's do the other one, 4 cubed for c sub 6 over 6 factorial c sub 0 x to the 6th. Okay, so those are the even ones, and plus, let's see if I can squeeze in the odd ones here. So c sub 1 all alone, or excuse me, it's going to be c1x. I apologize for that. So the first term will always have, for involving c1, will always have x to the first involved. Okay, so I made that mistake here. Everything else is fine. Okay, so we get the c1x, and then plus c3 was 4 over call that 3 factorial times c1x cubed plus, okay, so I call it the 3 times 2, 3 factorial, plus c5, 4 squared, 5 over 5 factorial, c1 x to the 5th. Let me squeeze in one more here. Plus c7 was 4 cubed over 7 factorial, c1 x to the 7th, plus dot dot dot. Alright, sorry for squeezing everything in there. Should have gave myself more room, but that worked. Alright, so now the even ones. Factor out of c sub 0 from these evens, and we have 1 plus 4x squared over 2 factorial plus 4 squared x to the 4th over 4 factorial plus 4 cubed x to the 6th over 6 factorial, and so on. Then plus the c1 factored out of these terms. And we have x plus 4 over 3 factorial x cubed plus 4 squared. Well, let's write that, okay, maybe better written as because we have to put this in terms of an elementary function. So maybe like I wrote the previous ones with the x's in the numerator. So let's say plus 4x cubed over 3 factorial plus 4 squared x to the 5th over 5 factorial, and then plus 4 cubed x to the 7th over 7 factorial, and so on. Okay, so now to our table. So as elementary functions, we're looking for patterns of even factorials as well as sums. Let's see, this is a difference. Here's continuous sums, even factorials. Let's check the powers. 1, oops, I'm pointing to, sorry. Okay, so I'm looking at comparing this first one to what we have available. And I'm noticing about the factorials in the denominator. Okay, even factorials, but there's a difference here, alternating signs. Here's even factorials with sums. So it looks like we're leaning in this direction. Let's check the powers. See, it goes 1x squared x to the 4th. That's what we have, 1x squared x to the 4th, and so on. So it looks like that, but the 4 is the issue. But remember, we dealt with this situation earlier. What we could do is write this as c sub 0, 1 plus, we could express the 4 as 2 squared x squared. And then express this 4 that's squared as 2 to the 4th over x to the 4th. Then express this 4 as 2 to the 6th, x to the 6th. Okay, so that's going to allow us to write this out as an infinite sum, fitting that form, once we group the 2's and the x's together. This one here, similarly, we could do the same thing, but notice that this would be 2 squared. Let's do it. This would be 2 squared x cubed over 3 factorial, and then plus 2 to the 4th x to the 5th over 5 factorial, plus 2 to the 7th, or excuse me, 2 to the 6th, x to the 6th over 7 factorial, x to the 7th, I apologize, over 7 factorial, and so on. Okay, and let's check that one out. Now it's odd factorials in the denominator, and it's a sum. And we have that for the hyperbolic sign, it looks like. Starts with an x, okay, and the power is x cubed, x to the 5th. Seem to be matching. But the problem is the powers on the 2 don't match the power on the x. So we saw this trick before where what we could do is multiply inside by 2. So multiply everything by 2, so distribute a 2 on the inside. But then to compensate, we'd have to multiply the outside by 1/2. So now we could express this as y equaling c sub 0 times 1 plus, okay, now we could say 2x quantity squared over 2 factorial plus 2x quantity to the 4th over 4 factorial plus 2x quantity to the 6th over 6 factorial, and so on, and then plus the 1/2 c sub 1, and then this would be 2x quantity to the 1st, plus, now there's 3 factors of 2, so 2x quantity cubed over 3 factorial. Similarly, plus, now there's 5 factors here of 2, so 2x quantity to the 5th over 5 factorial, and then plus, now there's 7 factors of x, there's 2 to the 6th, and another 2x quantity to the 7th over 7 factorial, and so on. So, just cheat here and grab another sheet of paper to finish this off. So extending this, we get that y is equal to c sub 0 times, okay, then we could express this as an infinite sum. And it's the sum as n goes from 0 to infinity of, okay, it looks like definitely a 2n factorial in the denominator. Here, I'm going to build it first, and then we'll check and make sure it matches what we thought. And then instead of an x, it looks like a 2x to the nth as a quantity to the nth in the numerator. And then we've got 1/2 c sub 1, and we'll worry about this sum in a moment. Or actually, no, let's take care of it now. So now we've got odd factorials. So that's 2n plus 1 as a quantity factorial. And then odd powers on 2x. So 2x is a quantity raised to the 2n plus 1 power. Okay, and then back to our little table. And looking at either the polynomial expansion or the summation notation, Recall we were on the, you could look at the polynomial expansion here, 1 plus 2x squared over 2 factorial. So there's 1, there's 2x squared over 2 factorial, 2x to the 4th over 4 factorial. So that's hyperbolic cosine of x, where x is 2x. You could see it in the summation notation even better. So this would be y is c sub 0 hyperbolic cosine of 2x. And then we have plus 1/2 c sub 1. And this one I believe was the hyperbolic sine we were working with. And look at the polynomial expansion. 2x to the first. There's x, which is 2x to the first. X cubed over 3 factorial. 2x as a quantity cubed over 3 factorial. 2x as a quantity to the 5th over 5 factorial. Everything's matching to be the hyperbolic sine of x, but where x is 2x. So therefore 1/2 c sub 1 hyperbolic sine of 2x. Okay, so one more topic left. Series solutions near what we call ordinary points. And that'll be the end of the course. And then we'll have review sheets for you, and just watch the announcements in Blackboard and your T-Wolves email, and we'll finish off the semesters soon enough.